Hello, this is Kyle Ormsby again. We're in the probability segment of Math 113, and this is lecture 4. Today's key ideas are the following two concepts, namely those of random variables and also that of expected value. So by the end of today's lecture, you ought to be able to answer questions like, should I play the lottery? More specifically, should you invest your entire life savings into the lottery? You'll also be able to answer questions like, if I take a random permutation of a finite set, how many fixed points should I expect it to have? So we'll review fixed points and permutations and dig into that problem as well by the end of the lecture. Let's jump in to random variables right away. Definition here. A random variable is a function. It's a function whose domain is S, a sample space, and whose codomain is the real numbers. Okay, so capital X here, the random variable, assigns to each element of the sample space some number. That's all. Very general definition, and thus seems a little abstract, perhaps. But of course, we can apply this in lots of practical situations. So we have some sort of sample space, right? Maybe it's the sample space of video poker hands, and our random variable might tell us how much money we win for each video poker hand. That's, of course, a real number. Good. One thing that we want to understand once we're assigning numbers to each element of a sample space is what the average output is. That average output goes by the name expected value. So a second definition, given a random variable x, we'll go ahead and make a couple of definitions here. Given a random variable, let's let x of s denote the image of that random variable. So recall, that's all of the values which x takes when we let little s range through the entire sample space. Okay. Under these definitions, we can then say that the expected value, e of x, is by definition a summation over all elements of the image of that value y, which x takes, times the probability that our random variable is equal to y. Okay, this is called the expected value of x. Okay, let's spend a little bit of time unpacking this statement. Let's start with the sigma notation here. What in the world does this mean? Well, coming over here, here we're just adding up a bunch of terms, one for each element of the image, x of s. Right, so in that video poker example, right, maybe a straight flush is worth $100 and a royal flush is worth $1,000. Then 100 and 1,000 would be terms that appear in this sum. Associated with each of those terms is going to be that number, y, times this quantity, the probability that x equals y. So that notation is meant to be evocative, but it doesn't necessarily follow the conventions we've established for evaluating probability distributions. It must be the case that x equals y is shorthand for subset of our sample space. So here the probability x equals y is indeed the probability of the event that we have an element of the sample space such that the random variable evaluated there is equal to y. Okay, so once we're comfortable with summing over the image and also comfortable with interpreting this probability, we have a perfectly well-defined number which comes out as the expectation or average value of x. So let's see how expectation plays out in a pretty concrete example. I've recorded the formula here so we can remember it. Our example here will be one of a lottery, right? So how does this lottery work? In a lottery, this particular one, we choose 6 distinct numbers. The order in which we choose them does not matter. And we choose those numbers from 1 through 4. Okay, in order for the privilege of choosing these numbers, we have to pay $1. Okay, on the prescribed date, the lottery goes ahead and selects its own collection of 6 numbers. If our ticket matches those 6 numbers, then we win $1 million. So that's 1, 0, 0, 0, 0, 0, 0. This is kind of a stingy lottery. If we don't match all 6 numbers, we get nothing. Okay, let's ask a question. Should we invest in this lottery? Fair question. Can't win if you don't play. And we want the $1 million. But let's pause for a moment and think, good investment or not. So it turns out that the expected value of a random variable will answer that question. The random variable that we're interested in is one which takes tickets. Let's call those T for ticket. Let's let this equal, well, -1. T doesn't win. And it equals 999,999 if T does win. Okay, so we've taken some ticket. Our random variable spits out one of these numbers. Why does it spit out -1 if T does not win? Well, we've spent $1, and thus we've lost $1 overall when T does not win. If T does win, then we win $1 million, but we've paid $1. So the outcome is that we are $999,999 ahead of where we started. So this is a good random variable to consider. We'd like to compute its expectation, right? The image in this case, x of the set of tickets, is precisely the two output values, -1 and 999,999. Good. We'll need to take each of these outputs of x and multiply them by the event that that outcome happens, right? So the probability that x equals 999,999 is exactly the probability that we've selected the winning ticket. There's only one winner, and we're choosing our ticket where order doesn't matter here. We're choosing 6 numbers from a set of size 48. So we see that the total size of the sample space is 48. Choose 6. There's only one winner. So this is a rather large number, which I won't write out. This is the probability that x equals 999,999. Meanwhile, the probability that x equals -1 is, well, the complementary probability, right? It's the probability we choose a non-winner. So that's 48 choose 6 less 1 divided by 48 choose 6. Okay. So at this point, we can now write out the expected value. When we write out the expected value, we get that the expected value is -1, that's our first output of the function, times the probability that x equals -1, plus, we're taking the sum here, we now have the second output, 999,999, times the probability of that outcome, which is 1 over 48 choose 6. Okay, if we grab our calculator or computer, we can produce a decimal approximation of this number, and it's approximately -0.918. Okay, how should we interpret this expected value? Well, it tells us that if we buy lots and lots of lotto tickets, not necessarily just one, but many, then in average, we expect to lose about 92 cents on each ticket. Okay, so if, for instance, we bought 1,000 of these things, then we'd lose about $920 on our investment. So not a good idea. We probably should not play this lottery. Expected values are oftentimes quite a bit harder to compute than the example that we just saw, but it turns out that they combine in various ways, and if we can compute the simpler pieces, then we can recombine them and get the value we're interested in. So let's think a little bit about operations on expected values. Sorry, on random variables. Okay, so here x and y will be random variables, and c will be a real number. Then we can define new random variables, which are called the sum of x and y, the product of x and y, and the scaling of x by c. These are all new functions from s to r, i.e. new random variables. We can do so via the following formulas. Where s, little s, is an element of our sample space. So how should we define the sum of two random variables evaluated at s? Well, remember that x and y each spit out a real number. And we certainly know how to add real numbers. So this has a natural definition as x of s plus y of s. Similarly, if we have the product of two random variables, then we ought to evaluate each random variable and take the product. And finally, in order to scale by a real number, cx times s, evaluated at s. We ought to evaluate x at s, that's some real number, and then multiply by c. These are simple definitions. For those of you who have seen some linear algebra, note that this operation here and this one actually do make the set of random variables into a vector space. So we're interested now in how to compute the expected value of combinations of random variables. And it turns out that expectation has an unexpected property, namely linearity. Okay, again, for those who are taking or have taken linear algebra, this is actually saying that expected value is a linear transformation from the vector space of expected values to, of random variables to the one-dimensional real vector space R. You don't need to know that terminology whatsoever to take this class. Linearity is also just the following theorem that I'm about to state. So here x and y are random variables, and c is some real number. Good. Then it turns out that the expected value of the sum of these random variables is the expectation of x plus the expectation of y. So here E transforms a sum into a sum. Of course, this is a sum of random variables, and here we're taking the sum of real numbers. Also, when we take the expected value of c times x, this becomes c times the expected value of x. So again, let's note that inside of the parentheses here, we have the scaling of a random variable. We take its expectation, and now on the other side of the equality, we're multiplying two real numbers, c and the expected value of x. So we're not going to prove this theorem today. I did produce a reading supplement, which includes the proof, and you're encouraged to read through that and try to understand the details. It's not really that hard. There's a significant amount of wrangling of summation symbols and some clever grouping of terms. It all depends on a lemma, which re-expresses expected value in a different way. A warning now. Here we see how expected value plays very nicely with summation and scaling of random variables. Expected value does not play well with product of random variables. In particular, the expectation of x times y is not the expectation of x times the expectation of y. So while linearity has two nice ways that these things play together, do not try to apply this purported product rule. Linearity is a really powerful tool. So here's a theorem that we'll prove using it, which is about the statistics or probability theory of permutations. So it states that the expected number of fixed points of a permutation of 1 through n here n is bigger than 0, is 1. Okay, let's prove this using linearity of expected value. So first let's recall what's going on here, that a permutation say pi, that's of course a function from n to n, which is a bijection, right? This has I in n as a fixed point, by definition, when pi of I is equal to I. So we see that as a function, pi isn't moving I around, it's fixing it, and that's why we call this a fixed point. Okay, given that this is how fixed points work, it's fairly natural to look at the following random variables, xi. These go from our sample space, the set of permutations of 1 through n, and land in the real numbers. It takes a permutation pi to either the value 1 if pi of I is equal to I, in other words, I is a fixed point of pi, or to 0 otherwise. I is not a fixed point of pi. Okay, this is a well-defined function on our sample space. And when we add up all of these x sub i's, we get something interesting. So let's let x equal x1 plus x2 plus xn. We see that when we evaluate x on a permutation, well, for each fixed point, we add 1 to the value of x. And when we don't have a fixed point, we add nothing. So x is constructed such that x of a permutation is equal to the number of fixed points. And what we'd like to do now is compute the expectation of x. Doing that outright is quite difficult. But computing the expectation of xi, where I is some number from 1 to n, is actually fairly simple. So let's think about that. What is the expected value of xi? Okay, well, the image of xi is clearly just 1 or 0. So we'll have the value 1 times the probability that xi equals 1 plus the value 0 times the probability that xi equals 0. Okay, can we compute these probabilities? Sure, of course we can. For a random permutation of 1 through n, pi of I is equally likely to be any of the numbers 1 through n. There's only a 1 out of n chance that it will take the value I as opposed to any of the other n minus 1 values. So this is 1 times xi equals 0 when we take one of the other n minus 1 values. So that's 0 times n minus 1 over n. We see then that the expectation of xi is equal to 1 over n. Okay, thus, by linearity, the expectation of x, the random variable we're interested in, is the expectation of x1 plus the expectation of x2 plus etc. through the expectation of xn. And we see that this is simply n times 1 over n, which is equal to 1. So we've proven our theorem. We expect to have one fixed point in our permutation. Since n here was any natural number, it's fair, given this theorem, to say that if we're talking about a permutation of a non-empty finite set, no matter the size of that set, we expect that permutation to have one fixed point. Okay, so this is the power of linearity. That's all I have to say for today, and thanks for tuning in to Lecture 4 of our probability series.